Go. Hello and welcome back to Calculus 3, section 12.4, partial derivatives. So, we used to have in Calculus 1 and Calc 2, the domain was one-dimensional domain x, and we found the change in respect to that x. So it was d dx to find the derivative. Now we have infinitely many directions on x, y. So instead of dealing with all of those infinity of directions, the derivative at the point, we are going to focus only on two directions. And that's the direction in x direction, derivative in x direction, which is called partial derivative in respect to x, and the derivative in respect to y, which will be in the y direction. Now, there is a great graphic in a book, but I will try to draw as as much as possible. So imagine you are on the hill, right? And then, so this is your location right here. And then there is a path that goes this way maybe, and there was another path that comes in from here and goes that way, right? So these are the paths. So I'll say path in x direction and path in y direction. Now, if I am to, I'll use the pencil for this, make the coordinate system over here. Oh, I labeled this wrong. I wanted this to be x and this to be y, so swap these, the black x and y. There we go. So, what this path now, right, is going to have a tangent line that goes this way, and another tangent line, maybe blue one, let's use. There's my blue. Goes that way. So the red one will be partial derivative in respect to y, and the blue one is the partial derivative in respect to x. Partial derivative has this weird looking d. So I'm going to use the word regular, I guess. Not supposed to do that. Is regular derivative, right? So that's the d dx of your function. Now you have a partial derivative. And a partial derivative is this squiggly. And that's going to be partial derivative of x and y. And then you have another partial derivative. In respect to y. And we are focusing on these partial derivatives. When you are taking a partial derivative of x, you will regard y as a constant. Because, as you can see, down the blue path, the y doesn't change. Y stays fixed, and you are only changing the x. Please note that that's a 3D drawing, which means that your z as you walk up and down is changing, right? But location-wise, you are only allowed to change x or y, not both. So x or y, not both. So red one, you will be changing y, x. So for red one, x stays fixed, y and z are changing. For blue one, y stays fixed, x and z are changing. And again, the derivatives measure the change at the point, the instantaneous change at the point. So you are still looking at same rules from Calculus 1. On to the definition, because we all know that we have those limit definitions. Partial derivative of f of xy in respect to x is going to be the limit when age goes to 0 of f of x plus age comma y minus f of x y divided by age. So please note that if you are to erase all of the y's, you just get your basic x definition from Calc 1. Can you do that? Well, here, I'll kill all the y's. Do you see that this is exactly Calc 1 definition that you are supposed to know from Calc 1? 3.1 in your textbook now? And now I will go with the partial derivative of f in respect to y is limit age goes to 0 of f of x comma y plus age minus f of xy divided by age. So these are the definitions. And we could do those limit problems from Calc 1. But we know, because we are experienced with Calc 1, that doing the limits is not the way to take the derivatives, right? We memorize those shortcut formulas, and then we deal with that. So say you want to find the partial derivative in respect to x of a function x squared y cubed plus sine y. All right. You are looking for the derivative in respect to x. Well, all the y's are constant. So what do I have? It's going to be, if the y is constant, then I get to copy that. And I'm taking derivative in respect to x, so I have 2x there. So it better be 2xy cubed. I can do it here. 2xy cubed. And what's the derivative of sine y in respect to x? 0. It's plus 0. Because we said y is constant. If y is constant, then sine of y is also constant. And the derivative of constant is 0. So it's plus 0. And that ends this problem. We just focus on x's and keep all y's constant. Partial derivative in respect to x of xy e to the x plus 3x. What do you think we're going to do now? Anyone? Product rule. I hope you see two functions and they both have an x and they're multiplied. So it is a product rule. So we are going to now say that this is equal to copy the first, xy, derivative of e to the x is still e to the x, plus the derivative of xy is just y, because the derivative of x is 1, copy e to the x, and then plus 3. Same rules like earlier. Well, I'll just leave it. We're not going to be setting it equal to 0 in this problem anyway. Now, same problem, partial of y. Do we have product rule? Do we have product rule? No, it's a single y. Look. Same problem. In respect to y, we have the derivative of y is 1, so x e to the x, and then this has no y's, so it's all constant. Derivative of constant is 0. It's dead. That's it. Maybe you want to start these two examples because it's the same function with a different partial derivative taken. I have a question now for you. If I'm to write down the function x e to the xy, which derivative is easier to take? Partial x, partial y? Why? Yes. Easier is the partial derivative in respect to y because you do not have to do product rule. Partial derivative of x has a function times another function, and you have a product rule. Well, let's do it. So we start with the partial of x. We have product rule. Copy the first function. Derivative of the second is y e to the xy. Right? Because y is constant. When you take derivative of e to the, I don't know, 3x, you get 3e to the 3x. So y e to the xy plus copy the second times derivative of the first. Derivative of x is 1. And that's it. Now we can make this one nice. 1 plus xy. Right? You can do that. Yes. And now same problem, partial derivative of y. What's the answer? Anyone? X squared e to the... Great. Perfect. When you take the derivative of this, x is constant, so x gets dropped in front, but there was another x there, so x times x is x squared. Nice. All right, let's see. Well, let's just take some examples from the book because they have them. They are full of these wonderful examples that you are going to dread all the way through. For instance, what is the partial derivative of ln of x over y? Beautiful question. And then we're going to do also partial of y when you're done with x. Done? You wanna, I have a marker.
1 over x.
1 over x. Is that your final answer?
I think so.
Okay. How did you achieve 1 over x?
Like if you actually just do the sorry.
What?
You take the derivative of the ln, which would just give you 1 over x over y, and then you have to use the because you also have to take the derivative inside, you have to carry the y over, so that gives you since you have a y on top from the ln, and you also have a y on the bottom from the x over y, you end up with 1 over x.
So your answer is y over x, and his answer is 1 over x.
No, I said 1 over x.
Oh, 1 over x, okay. Now which way you did it?
1 over x?
Yeah.
I did 1 over y over x over y, and then I did the whole denominator rules, and then canceled the y's, and then got 1 over x.
Okay. So we have two different methods of solving the problem, and they both have 1 over x. Does anyone have anything else to offer? Yes, no? Let's go Calc3. Chris, what should we do?
You can put it up into ln x.
Yeah, there we go. And then ln y is just 0. See? That's why he's the SI over here, the boss, right? So you're right, when you can, you should, right? So you have this using basic ln rules, and you just get 1 over x from the first one. The second one only has a y variable. We are taking the derivative with respect to x. So ln y is a constant, and it dies in the derivative. Now it's immediately easy to see that the derivative in respect to y will be negative 1 over y. Very good. So you guys had the right answer. That's good. That was problem number 16 in your textbook. Let's see something else you're probably gonna love. Ooh. I mean, I don't know where they find these perfect examples, but the book is full of them. Problem 23. Let's find the partial derivative in respect to y of z squared tangent yz. You got this? Anyone?
Z to the third secant squared yz.
Yep.
Yes. I am absolutely dying. I don't know why I looked at my phone. My friend sent me the picture of he fixed the slipper. His son's flipper. And he said, the aesthetics doesn't matter, it works. I mean, come on. He does this stuff all the time. So I grew up with this guy. I mean, we go back to like 1993. So I met him in 1993. He had a very interesting group of friends. So they, one of those big boom boxes, and then we would go to the beach, and then we would take apart, and everyone else moves out right away, and then we have all the place, to ourselves, and then just have an awesome time. But so his son is 18. That was his flipper. Anyway, Calc 3. Anyway. That was the official shout out. How about the second partial derivative? Why not? You have already the first. So how about the second partial derivative of z squared tangent yz? So that means you have to take another derivative of this now. And that's going to be lots of fun. Because you have, more partial derivatives coming up.
Is it 2z to the fourth secant squared yz tan yz?
Maybe. I don't know. I haven't done it, but possible. Let's see. What others come up with. So since in respect to y, we can copy z cubed as the constant, and then we have secant squared. So the derivative of that is 2 secant yz to the first power. Then I have to take the derivative of the secant yz, which is the secant yz tangent yz, and then I have to take the derivative of the inside, which is z. So what do I have? I have 2z to the 4 secant squared yz tangent yz. Yeah. Yeah, that was an album by Nirvana a very long time ago. No one. Look at this. No one.
Why not?
+2. That's that. Some of you would know that there are differential equations where you look at the calculus 1 rate of change, the derivative, and you can write a differential equation that has a derivative. Absolutely, because you're taking that class. And some of you are done with differential equations, so you would know that as well. There is also a course called partial differential equations that will contain differential equations that contain partial derivatives. And those equations are much harder to solve, but are crucial for a lot of applied mathematics and engineering. One of the most famous equations ever written is the wave equation, which governs the motion of particle, and that motion is happening in space and time. So you will find the second derivative in that equation, second derivative in respect to time, a partial derivative in respect to time, and a second derivative in respect to space. So that's again something that we'll see. But let's just take a look at notation a little bit more. Notation. What do I have notation wise? Well, we have the z equals f of x y. So partial z partial x can be written as f and then little x on the bottom. So that's the first derivative, first partial derivative in respect to x. Or second derivative is just simply going to be written as fxx, like this. So that's the second derivative. And then we have the pair for the y derivatives. So partial z partial y is fy, and partial squared z over partial y squared, right? So that's the second derivative is fyy. And you know how to find these derivatives, because all you need to do is to find the first one, then you find the second one, then you find the third one, right? And the same rule like in Calc 1, where the third partial derivative is the first partial derivative of the second partial derivative. So you just link them. In order to find the seventh partial derivative, you have to have all previous 6 partial derivatives done to find the seventh one. So you can't skip. But then there is a notion of the mixed partial derivative, and that's new. I mean, all of this is new, but you know how to deal with partial derivatives, so mixed partial derivatives. And those are when you have fxy or fyx. Now this is obviously only if you have 2 variables. If you have 3 variables, then there are more combinations of this, clearly. So mixed partial derivatives, maybe I should just go one by one. So fxy means that you will first take the partial derivative of f in respect to x, and then you will hit that with the partial of y. Clearly it's a second derivative, because you are taking 2 derivatives. So partial derivative x is done first, and then y is done second. Or you can have partial derivative yx, where you will do y derivative first, and then x. Right, so start inside the parentheses and you go outwards. Now let's try a problem from mixed partial derivatives. So find, I said switch the color, there we go. Find fxy and fyx for fxy equals to x squared y minus 3 sine xy. So find both, and please check it with people next to you, around you. So what have you found interesting? Anyone? Have you found anything interesting? Same answer. And that is a theorem. Partial derivatives, mixed partial derivatives are the same. And that might really help you in solving some problems down the line. Because remember how we said, if you look at this problem here, if you start the problem with the xe to the xy, if you start a problem by taking the x derivative, you have to do product rule, but if you start taking the y derivative, you don't. So clearly there is a time saving there if you know the theorem. Well, let's first solve the problem and then write the theorem. So partial derivative in respect to x first is equal to 2xy minus derivative of sine is cosine xy, and then y goes out, so 3y cosine xy. And now to find, so this is just fx. And now to find fxy, I have to take the derivative of this in respect to y. So I have 2x here, and now I have the whole product rule going. That's going to be, because in taking respect to y, so I have copy 3y. The derivative of this is negative sine xy, and then I have to kick out x, so x in front, plus copy cosine xy times 3. There we go. So what's fxy? It's 2x plus 3xy, right, 3xy sine xy minus 3 cosine xy. And when I do this the other way, it better be the same answer. So this is the first. Maybe I can box it with a pencil. And now I'm doing the second part, which is partial f partial y. Start there. When I take partial y, I get x squared minus 3x cosine xy. And now I need to find, so this is equal to fy, right? And now fyx, so now I need to take derivative of this in respect to x, and I get 2x minus, and now I have the product rule here because you have x and x again. So copy the first, which is 3x, times derivative of the second, which is negative y sine xy, plus copy the cosine xy times 3. There we go. Close the parenthesis at the end, and I'll simplify, get the same thing. So we have 2x minus, and minus give me plus 3xy sine xy minus 3 cosine xy, and it's the same. So it doesn't matter, right? I mean, this is not a proof. This is an example for you to see something like this. And then we write the theorem for mixed partial derivatives. So assume that f is defined on an open set D. Assume that f is defined on an open set D in R2, and that mixed partial derivatives fxy and fyx exist. Oh, are continuous. Well, exist and are continuous. Throughout D. Then those partial derivatives are the same at all points in D. And I'm just going to change the shade of red and say, in parentheses, this works for more variables as well. So you have, let's say, fxyz, the same as fxzy, the same as fx fyzx equals to 3 dots. You know, write all of them out. So it doesn't matter in which. Now this is clearly different than if I had fxxy. I can do the third derivative, fourth derivative. So it's a lot of combinations that we can consider with this one. Actually, maybe I can, instead of z, I could put more. Let's put one more y instead of z. Maybe it makes more sense. So yx and yxy. So those are all the combinations, no more. You can take whatever amount of derivatives you want. So this is technically equivalent to the third derivative. You only have two variables, but it's equivalent to the third derivative. Ideal gas law. PV equals nRT, but they call it KT because n times r constants are in here. And now you can consider this. You have the pressure, volume, and the temperature, and then the constant that connects them. So if you are increasing the pressure and keeping the volume the same, then the temperature increases. You know that in the summer you are supposed to let some air out of the tires, and in the winter you're supposed to put more. Just want to see if anyone is just staring at me right now. So if you fill your tires in the summer full with air, right, to the maximum pressure that the tire will allow, in some cases 40 psi, 42, 50, depending on what tire you have, it's going to explode. You see those, exploded tires all over the road. So what happens is once you fill the tire all the way and can't expand anymore, right, volume-wise, it's just expanded all the way. As you drive, the tires get very hot, and it's summer, so there is the heat from friction, and also heat from the environment. You keep the volume, right, fixed. Pressure is already at the max. You keep increasing the temperature, pressure has to increase because volume is constant. And what you get with the tire, haboom, right? So you can't have high pressure inside the tires during the. Now in the winter, clearly, right, it's cold and everything, so it's good to have higher pressure. And you can find all the other applications of this. So now you can measure the change of pressure, right, with the partial derivative as you keep the volume constant, right, and the temperature, let the temperature change. So you can find the partial derivative of the pressure in respect to temperature for this equation, and you will do that, right, PV equal KT, and you can see from here that, right, the P, right, that's going to be the derivative. So you get your, well, what's the derivative of this in respect to temperature? So if V is constant, so if V is constant, right, then you will just find dP dt times the volume is equal to K, and then that's just T there. So you see that the change in pressure is inversely proportional to the volume. So change in pressure in time is inversely proportional to the volume. Now we actually use these things to design and study systems and predict the future, rather than build something and then just wait for complaints to come in to fix it. And now you can go and study, change of volume in respect to pressure, change of pressure in respect to time, change of volume in respect to time. You can study any of these changes that you might be interested in. So partial derivatives go, long way. You can read the entire example with all of the different parts. Still same theorem with continuity and differentiability. So if the function is differentiable, it is continuous. That's the best way to find a continuous function. Remember that you are supposed to check infinitely many points, which is really not practical. So you will actually check if the function is differentiable, and if you can differentiate the function, then it's continuous. That's another theorem. So I'll put over here theorem and say differentiability implies continuity. It doesn't work backwards, just one way street. And the proof is the same, like in Calc 1 you have the special function, you plug that in and it works. Let's take a look at some wonderful examples. So this is more than two variables. Problem 51. Find the partial derivative of your function f in respect to, let's say, I don't know, y, it doesn't matter, pick whatever. It will be best if you just pick random. W squared xy squared plus xy cubed z squared. So, no equal, oh my god. What am I doing? Find the partial derivative of this. I completely wrote the wrong notation there. See you next week. See you next week.
All right.
So this was, right, no other problem. 2w squared xy plus 2xy z squared. That one. Now you can factor. Yes, we are going to set this equal to 0 and have it as one of the many equations to solve in a system of nonlinear equations to work out Lagrange multipliers, which are the version of optimization problems on steroids. From, you remember the optimization problems, minimization and max? Yeah, that one. This one is just going to be much more interesting, dare I say. So factor these things for ease of equal to 0 later. Oh, welcome back. Now, without actually, working out these examples, this is where you are going to wreck a few hours. Look, it's a wonderful example. Miscellaneous partial derivatives. Compute the first partial derivatives of the following function. When they say first partial derivatives, you have two variables, so there's partial x, partial y, right? Partial x, partial y, partial z, so this one has 3. And again, 3. And you can see, right, it's going to take a little bit of time to do. But, experience in doing these problems is very important. I'll just point out the inverse tangent and leave it there. Yes?
So when it says the first partial derivative, does that mean in respect to x or y?
Both.
Oh, both.
So you do one and then you do the other. And in some cases, you are going to learn a lot from these exercises because some of them are symmetric. So you will develop the skill to see when you have a symmetric function that the derivatives just swap the variables around. And which variables swap, which variables stay where they are. So, for instance, if you look at the 68, it's not symmetric. If you look at 67, not symmetric. 64, symmetric. Because you don't have any differences. You see all x's and y's, they're together. And also for 65, it's symmetric. And also for 66, it's symmetric. But 67, 68 are not symmetric. Now, what does that mean? Symmetric, not symmetric, and so on, and how well, obviously, you should be practicing the 3 problems above, right, the first 3, and then practice the second 3, and you will see the differences in their answers. Now, I'm going to make up a problem, because I don't want to ruin that for you, because it's probably going to take about, an hour for you to enjoy all of it and make the conclusions. So how about I come up with something? So what is symmetric? Let's say I have f of xy, and I want to create something symmetric, so I'll make x squared plus y squared, everything cubed, minus xy. So this would be symmetric, right? Now, I can make this asymmetric easily. I can just put a square on y, is no longer symmetric. But if I put a square on x, it becomes symmetric. Do you see that? So they have to have this balance. Now let's take a look at the partial of x in this case. So we clearly have 3x squared plus y squared squared, and then times the derivative of the inside, which is partial of x, so it's 2x, and then y squared just dies. And then minus, you have partial of x is just y. Do we all agree on this derivative? You have a cube goes down, becomes squared, derivative of the inside goes out, and then minus, right? So now partial f partial y is going to be, going back again, 3 x squared plus y squared, everything squared, because 3 minus 1 is 2, times the derivative of the inside. Well, I'm taking derivative in respect to y, x dies, so I have just times 2y, minus, and derivative of the thingy is x. You see what happens? These chain derivatives are different, but they are the same form, and this guy over here they're different, but they're the same form. So that happens when you have symmetric equation. When you have asymmetric equation, they don't have this quote-unquote one-to-one correspondence, where this lines up and this lines up, and this lines up in a form, not necessarily in the variable, because we are taking the derivative in different things. So now, if you're truly interested in learning these things and you want to push your life further in mathematics, just by adding a little square over here will do it. You will see that doing this part over here, you would have a y squared, and over here you would have a single x. So if you have a y squared and a single x, they don't have the same form anymore. So that square would break this type of symmetry. This is very useful for problems that are long to compute but repetitive. And you can just exploit the symmetry. Now, it takes time to learn what the symmetry looks like. And that's, symmetry in equations is not the same as the symmetry in graphing things. So, again, that's symmetric because it's negative xy. And then this is symmetric, right? Because it's tangent of these two. And when you hit this with x, you'll have 2x. If you hit it with y, you'll have 2y. This is symmetric again. Look, x plus y, they're the same. And then x plus y, again, the same. Now this one, not symmetric, because the x and the y and z is in the exponent. So clearly, and this is also clear all over the place. And yeah, I just shut everything down and just leave. Bye. I have